Hi there, this is Vector Statics, Introduction to Vectors, and basically I'm just going to walk you through some general knowledge on vectors and how to deal with them. So, let's start off. What are vectors? Well, vectors, essentially in math what they're used is, they're used to determine both the direction and the magnitude. And I can just give you a quick arbitrary vector. We'll give you this one. And I'll call it V. This is vector V. And first of all, I just wanted to point out that what if we were on an X and Y axes? How would we represent this in terms of X and Y? And what you can do is you can actually break this down into X and Y's, and I'll just call this A and B. So when you break it down, this would be AI plus BJ hat. Now, I hat is just used, it's the X component of a vector. So I'm just going to kind of associate this. I don't know how to say associate. Let's just say it's not really equal. I just wanted to show that they're associated in some way. And usually when it's a vector, there's a little hat over it. Whoa, sorry. This is Z. So sometimes you'll see Z hat, Y hat, or X hat. And all that means is that that's saying the direction only. And no matter what, these directions will, if you were to multiply, use the Pythagorean theorem, see, let's just say total, let's say d squared, that's the total distance of I squared plus j squared plus k squared, that d is going to equal 1. So the idea is that it's not supposed to affect the magnitude, it's just supposed to give us a direction. So let's start off. How do we add vectors? And there's several techniques of doing it. Let's just start off with a few of them. Let's say we have a vector right here. I'm going to call this spot O, and let's see, this direction, I'm going to call that vector M, and this vector right here as S, vector S. So what if I wanted to add these vectors up? Basically, this technique utilizes extension lines, which essentially form a parallelogram. Now, what I want you to do is look at this vector M, and I want you to notice the angle that it's sitting at. And what I want you to do is I want you to extend it over here at the tip of S. So notice how I'm extending it in the same direction, as the same angle almost as M is. And I want you to do the same thing with S to M. So notice how we're forming a parallelogram. This point, and I'm just going to call it point X, is actually the resultant of adding M plus S. So if I were to draw a line right here, and call this R, we could say that R hat equals M hat plus S hat. So there you go. And that's using what I like to call just the parallelogram technique. Some people like to use different techniques. One of them is essentially just putting the additive vectors, connecting them almost like in series. So a way that we could look at that, I'll just look at the exact same situation, right? You have O, let's say you have S. Okay, now if we wanted to add M onto S, we would no longer attach it here. We don't attach it at the O, but we would attach it right here at the s. So our vector m is added on. Now you see that you have a triangle here, which consequently turns into R. And yes, to find the magnitude of R, you can also take, you can do the Pythagorean theorem as well. So, I'm just going to call it R squared equals the magnitude of m squared plus the magnitude of s squared. So Pythagorean theorem still applies here. So yeah, that's head to tail kind of addition. And finally, what you can do, and this is probably what you'll end up doing most of all, is you can break it down. So I'm going to say just break it down to components. Just like we did in the beginning. Essentially, I'm just going to give you values. You don't know from this picture up here. We don't know any like values or anything, but I'll just give you some. Let's say if S is 1.5i and minus 1.5j. Since it's 2D, there is no k value, and we'll get into that 3D values later on. But the concepts are exactly the same. 1.5i, once again, but then what if plus 2.5j? It's really going up. So what you can actually do is you could just add these two together if you're adding s plus m. You can do that. You can just add these two up. So quite literally, I just draw a line and take it into basic arithmetic, which is just going to be 3i hat plus 1j. Whenever you see 1j, you can actually just write that as j. So our resultant, it's fair enough to say our resultant is 3i plus j. And that's our resultant force. Or resultant vector, I should say. Now, one thing that you need to realize is that statics is about non-moving parts. Therefore, when you think of statics, or something being static, you have to think of the summation of force to equal 0. So, it's pretty much a fair statement to say that we need to find a way to zero out vectors. So we need to zero out vectors, right? Well, think of it as you did back in elementary school when you're adding and subtracting, You had basically, well, r plus a negative r, or essentially r minus r, right, is equal to 0. So that's how we're going to zero it out. So essentially you just need a negative form of your r vector, which negative r vector will just equal, you just multiply everything by -1. So and what does that look like? Like, some people are not exactly sure what that means, but notice that when you just multiply everything by 1, that's just the exact opposite direction as well. It's the same magnitude, because if you perform the Pythagorean theorem on this, -3 squared plus 1 squared, you're still getting the same thing, right? That's square root of essentially 10. That's the square root of 10. What did we have before? 3 squared plus 1 squared, it's the same thing. See how the magnitude's the same? So anyway, I just want you to notice that essentially the magnitude's the same. If this were r right here, and this were negative r right here, you can see how essentially that's equal and opposite, and that's not going anywhere. They cancel each other out. And I'll follow up and do more on this topic in the next video, so we'll give you some examples, and they're really fun. Have a good one.